Hello and welcome to another video, and in this one we're going to take a look at how to code a basic ray tracer. But before we get into that, I'm going to quickly show a thing about the rasterizer that we've been working on in the past before we move on to this. So let's get started. I'm going to go into Blender actually, and this is to show that right now if we go to our our current Uh, let's 1 second. All right, there we go. If we go to our current, what we have for our rasterizer, we're just rendering a couple of triangles on there. In order to make this a little bit more take it to the next level and to help you guys for your final, um, one good idea would be to render something that you made in Blender. And like the first step to that, I would just kind of like to lead you guys to it would be to go to Blender, go to our general. And I'm just going to show it for this cube, but this will, it's applicable, and this is how you'd want to do it for any object that you make. And I would suggest, try to make it somewhat simple, yet, it's a nice, meaningful object. You don't want to overcomplicate it, then it's not going to render out really nicely. So yeah, what we're going to do is we have our cube file, export. We're going to export this as a wavefront OBJ. And then we want to have triangulated mesh on, so remember that. Um, and then we are gonna go, figure out where we're gonna store it. For me, it's class, and I believe it's in here. So I'm just gonna call it cube.obj export wavefront. All right, this should be good. Perfect. So let's go to that. So it has a MTL and OBJ. MTL is for like the materials, the color. And I would say these both are important because the MTL allows you to that's how you can color your object. So that you'll render. And then this OBJ is how you'll render the actual object. All right. Um, Getting back to it. So yeah, this one before we actually work with it, we need to kind of prepare the file. We don't need these extra things right here, you see. We don't need these, but you can, because the way you code, it just depends upon how you code it. I'm just trying to simplify it. You can code to ignore these things. But yeah, the idea is if you want to make it easier on yourself, just go ahead and remove those things. What we want to focus on is this right here. These are your vertices. These are your vertex normals. This is your UV coordinates, and these are the faces. So yep. So this is why you want to have that's why you want to do the triangulate mesh option in Blender, and that will put it to just 3 of these instead instead of generally it would come out as 4. That's why you want to have um the triangulate mesh option in Blender instead of just exporting it right away. So yeah. So when parsing through, basically the idea is you check like the first character for the different V, V for the vertice, VN for vertex normal, VT for UV coordinates, and F for faces. So you just want to get that, and that look out for that, and that's how you would kind of parse it and separate it through. And how you would do this is, you can call it OBJ, and um, second. Oh, actually, hold up. No, you don't want to do that. we go here to my folder. I want to create a new file. It's going to be a JavaScript file. It's going to be called cube obj.js. So I'm going to make this file right here. Then I'm going to do obj equals like that. Kind of like how we did for our fragment and vertex shader. Then copy all of this and plop it in here. And there you go. So now what you want to do is you want to, in your index.html, just like how we do here, you just go ahead and add, um, 1 second. All right. So you just want to go here and then just import it here to obj.js. And now you'll be able to read obj and then you'll be able to parse through it. So that's it for the quick little update on what you guys should work on in the future, is trying to parse that. You can start with the cube or whatever the basic objects, then eventually you should be able to do whatever other model you might have made in Blender. So yeah, now that we got that, let's go ahead and code our ray tracer. Index.html. If I can scroll. All right, there we go. All right, so this code, it'll implement a basic ray tracer that'll render a red triangle on a black background by simulating how rays interact with the 3D triangle. So that's what you see in our what we want to achieve on the end product here. So let's go back to the code and let's get started. Our basic, HTML boilerplate. Got our doc type HTML, then you got HTML. Then we're gonna have our head, and here we're gonna have a title. We're just gonna call it Ray Tracer 1.0, and then for the head, we're gonna have our body, and in here, so we're still part of the boilerplate section. We always make our canvas, call it ID, give it an ID called can. That's how it generally is. You guys should be familiar with that by now. Next, we're going to go to our script section. And in here, still boilerplate stuff, where we go let canvas equals document dot query selector, and making our 2D canvas and calling that that we made there. Yeah, JavaScript's not, the current version is not too strict on this, but I would generally just go with the semicolons at the end of each line. And then now we're gonna create the canvas, 2D canvas, with the dimension 640 by 640 pixels like we have been doing. So canvas.width equals 640. Canvas.height equals 640. And then we go to let context, the variables used to draw on the canvas. So let context equal canvas dot get context. We're doing 2D. All right, so that's just like how we have been doing it previously for our rasterizer as well. Uh, select the canvas element, and then we set its dimensions, the canvas width and height. We get the 2D rendering context for the canvas. Now we're gonna go ahead and define some constants for the array indices, so it'll be easier for us to read. So we're gonna do const x equals 0, y equals 1. These are commas, not semicolons. They should be. and z equals 2. Right, now that we have set up our constants, I'm gonna go back to the constants here. Now that we have set that up, we're gonna go ahead and create some mathematical functions like helper functions, and the functions we're gonna create are add, minus, dot, or minus, subtract, dot, cross dot, and then cross, scale, length, and normalize. And they'll be defined to perform vector math. So yeah, so that's why they are, you have to make separate functions instead of just doing plus minus. This will help simplify things. And then this is because these are all essential for the ray tracing calculations. So yeah, let's get to that. So the first one we're gonna do is addition. A lot of these are kind of gonna be copy paste because it's once you do the first one, then the rest of them are pretty similar. So yeah, let's go ahead, do function add, and then we're gonna do p1. So this is to add two 3D vectors. So we're gonna do p1, p2 parameters. Then what we're gonna return is need to do a square bracket p1x plus p2x. Then we need to do p1y plus p2y. So you can see the pattern. We just need to do the same for z. p1z plus p2z. All right. Now let's make the subtraction function. But this we're just gonna copy paste it. But we're gonna have to do a slight flip flop so we can subtract p1 from p2. We're gonna change this to or minus function. Doesn't matter. You can call it whatever you would like. Just gotta change the 2. Subtract it, and then just go down the line and change these. All right. So now our minus function is ready. I believe, no, I made a mistake here. This has to be 1. All right, there we go. Got to look out for those. Now we're gonna make our dot product function, and it'll compute the dot product of two 3D vectors. So we're gonna do function dot p1, p2, and then same old return. But yeah, to make our job easier, we're just gonna copy from here, put it right there. But we just need to change these to times, and then change the commas to plus. And that should be that for the dot product function. Yes. All right, now let's move on to our cross product function. This will compute the cross product of two 3D vectors. So cross p1, p2, and then we'll return p1y times p2z minus p1z times p2y. Nope. Just gonna do a comma. I keep getting these commas and semicolons mixed up, but yes. So now we just need to duplicate it 3 more times or 2 more times. And then it'll be p1z. We need to change this. Be x P1x times P2z. Right. Now that, put a semicolon here. And then our cross product function is ready. Now we're going to do a function to scale a vector by a scalar value. So function, now the next few ones we're going to do is a lot more simpler. Do p, s, scalar value, p is the vector that we're going to scale. So we're going to do return, square bracket, p, x in the vector times s. So we just scale each of the x, y, z in the vector by the scalar value. And that's our scale function. Next, we got our length function. So this will compute the length of a vector. So we're going to go ahead, call it length. And then we pass in our vector. And then we'll return math. If I can spell, return math dot sqrt. And then go ahead and do p, get our x. We'll square it. And then add it. And then, so we should need to do the same for y and z. Just square them and add them. Alright, so that's it for the length function. Finally, we have our normalize function. Alright, and we're going to pass in our vector here again. So this one will normalize a vector to make its length equal to 1. So, do return, if I can spell return. But in order to do that, we need to use the length function. So we're going to do p, we're going to get the x in the vector, and then go length, pass in the vector, divide it. So we're going to get the x and then divide it by the length of the vector. And then we're just going to do the same for y and z. So I'm just going to copy paste it, save some time, x, y, and z. And there we go. So now all of our helper functions are ready. That's definitely like half of the code right there is helper functions, because this then significantly simplifies what we're going to do next, which is just loop through each pixel on the canvas and do our ray tracing work. Alright, so now next thing to do is define the vertices of the triangle we're going to render in the 3D space. So yeah, we're going to define it using the vertices. Let's, one second. All right, so you can pretty much pick however you want your triangle to be. Um, and this is what I'm gonna go with. It's gonna be just slightly different, nothing big, just a smaller triangle. I'm gonna go with. So yeah, we're gonna do negative 0.5, comma, negative 0.5, negative 1. And then we can just copy this. And I'm gonna go take this negative off here. Take this negative off here. Take this negative off here. All right, perfect. So now our vertices are ready. Vertex A, vertex B, vertex C. I'm gonna explain in a second here where these vertices are. So in order to do that, I guess let's just quickly run this. It's gonna be nothing is gonna show up, but um, ideally our vertices are, we have, if we go back here real quick, we have negative zero point 0.5 and negative zero point 0.5. So that is gonna be, it's gonna, let's just say like right here, is gonna go negative zero point 0.5 this way, and it's gonna go negative zero point 0.5 up. So that's that point. The next point we have is negative zero point 0.5, zero point 0.5. So that's gonna be negative zero point 0.5, and it's gonna go down 0.5. So then we have that. Then we have 0.5, 0.5. So we'll start from 0, go 0.5 this way, 0.5 down. So then we'll have a triangle like that. Alright? So that's what we're gonna work towards, is rendering that. Alright. So now all we have left is a double for loop. I know it sounds simple, but there's gonna be a lot that goes into it that actually does that calculation. But to put it simply, that's what we have left. And this is what will do all the array plane intersection, the triangle inside test, and the pixel coloring. So this code will do a loop, and this will loop through every pixel on the canvas, px and py. So, like I said, this will loop. I guess I'll, as I code it, I'll explain more of it. So let's start with for. We're going to let px equals 0, semicolon, px is less than our 640 with px plus plus. Then I'm going to start a bracket. And then now we'll do for py, let py equal 0, py less than 640, py plus plus. Alright, and then we start this. Perfect. So we got, so this will loop through each pixel on our canvas. So let's go ahead and like that. Okay. So we have different parts here. We have three parts, or I guess four, you can say. So let's begin with the first part. The first part is to compute the ray origin and the direction, which the origin is O and the direction is R. So we're gonna go let x3 equal px px divided by 640 times 2 minus 1. Okay, so this will map pixel x coordinate to negative 1, 1. And then we're just going to copy paste this and do the same for y3. But we just need to rename it. Rename this to py. And this will map pixel y coordinate to negative 1, 1. Alright, so now that we have those two, we're going to go let p equals, so this will be the point on the view plane. We're going to go x3 comma y3 comma negative 1. So now that we have that, next we'll do the ray origin, the camera position for it. So let O equals, just going to be 0, 0, 0. Finally, we'll do the ray direction, which will be normalized, which will be let R equals normalize. We're going to call our normalize function. Start using the handy helper functions. And we're going to pass in our O, which is the ray origin. Then the P, which is the point on the view plane. So that is part 1. Okay? Uh, so yeah, let's go here. Yeah, so for part one, we're rays generated from the camera origin 0, 0, 0 through the pixels position on a virtual view plane. And then the ray's direction is normalized to ensure the you consistently calculate it. And it's for each pixel it's done. All right, next, um, the next section is the ray plane intersection. So first, part two, we're gonna begin with let n equals 0, 0, 1. This is the plane normal and it'll face along the z-axis. Next is let d equals negative of the dot product. So we're going to use that function. We're going to pass in our n and we're going to pass in our triangle, which that we made right here. So we're going to pass the 0, and this is the plane equation constant. A lot of these right here is just so Dr. Ricks in class went over the math, just like written by hand, and this is just kind of like translating what he went over to code. So I highly suggest that till you look at his notes that he has posted, and this will kind of help make more sense. Right. Getting back to the coding, next we're gonna do let t equal. I'm gonna make a bracket here. D negative d minus dot. We're gonna do the dot product of n, which is our plane normal, and our O, which is our ray origin, divided by the dot product of our n, comma, and our plane normal, and the ray direction. So what this does, it solves for the t intersection distance. And finally, for part two, we're going to do let p equals add our O, ray origin, and then scaled r, the ray direction, and the intersection distance that we just calculated. And what this line does, it computes the intersection point P. All right. So that's it for part two. To kind of recap the triangle, it lies on a plane in 3 space. This code will calculate where the ray intersects this plane using the plane equation and the ray equation. All right. So next, let's move on to part three, our final big part. And this will check if the intersection point is inside the triangle. And then only we'll be like, okay, let's render this triangle if it's inside it. So, this one, I'm going to start with let v0 equal minus function, and then we're going to pass the edges of the triangle. So the first edge we're going to pass is AB. So we're going to go triangle, or I guess it'd be flip BA, I guess. So yeah, triangle and 0. Then we're just gonna copy paste this. We just need this 2 more times. We're gonna go V1, V2. So now this one will be the edge BC or CB. Yeah. All right, because it's 0, 1, 2, and we have it as ABC. So yeah, I guess I'm just flipping it. But yeah. Then the final one is the edge AC. So 0, 2, 1 second, I forgot to fix this. This should be, yeah, it should be. So we have edge BA, BC, CAC. Yep. All right. Next, we need to do the vector. So we're going to let P0 equal minus, we pass in our the intersection point that we got up on part 2, end of part 2. So we'll pass it in. We're gonna again have P0, P1, P2, like how we had V0, V1, V2. And this we're gonna first pass in our vertex A, so we can find the vector from A to P. And then we just copy paste this, and then we just need to change P0 to P1 and P2, as well as triangle. We need to do the vector from B to P, or B to P, and B to C. And then finally, a last part of the part 3 is the cross product. So we're gonna do let C0 equals cross. We're gonna pass in our vector from A to P, as well as our edge from B to A. And this will provide us the cross product for the edge B to A. And then we just copy paste this, and we go V1 or C1, C2. Change this to P1, P2. Change this to V1, V2. So here you get the cross product for the edge BA. Here you get the cross product for edge CB. Here you get the cross product for edge AC. All right, that's it for the part 1, part 2, and part 3. And to kind of recap this part 3, what part 3 does is the second part 3, it checks if the intersection point is inside the triangle. So first it begins by, we find the intersection point in the previous part. Then this one checks if the point lies inside the triangle using the cross product. So first we calculate the vectors along the triangle's edges and vectors from the triangle's vertices to the intersection point. The cross products of the vectors are then we'll use that to determine if the intersection point is inside the triangle. So that's where now we're going to actually check if all the cross products point in the same direction. So let's go ahead and do that. We're pretty much the tail end here. So to do an if statement, we do if C0 and then the Z is greater than or equal to 0. And then now we do an AND, because it needs to be all of them. And then we go ahead and copy paste this, remove the second AND here. We need to change to C1 and change this to C2. Alright. Now, if it goes into this statement, then we know the point is inside the triangle. So, we're going to do context, for inside of the triangle, we're going to context fill style, do RGB. I'm going to go with red color, like I showed. we go. And now we need to actually draw the pixel. That's where you do context.fill rect. Pass in the px, py, 1, 1. There we go. Misspelled this. And then we also need to do an else statement. If we have, if that doesn't, if it's not pointing, if it's pointing outside of the triangle, then we just copy paste this line right here. If it's pointing outside of the triangle, then we color black. Alright, so let's just recap real quick. I know you guys want to look if the code actually worked, but before we do that, I just want to recap real quick. And so yeah, first if statement is if the intersection point is inside the triangle, the pixel is colored red. If the else is there to take care of if the point is outside the triangle, we want the rest of the canvas to be colored black. So yeah, the result we should get is the canvas should display a red triangle on a black background. And it'll be rendered by simulating how rays interact with the triangle in the 3D space. So let's go ahead and look at it. We have an error, I would think. Cannot pass P before initialization. Might have. Ooh, let's see. Let P. What did I do wrong there? One second. Alright, I have found the error. So, first one, when we go to here, when we do our normalize uh, for uh, for our ray direction, I put a capital P. That's something you want to be aware of. It's the normal P right here. That it's this. This is what you want to pass in because we don't even get to this. That's what I was trying to do there. We want to pass in our point on the view plane, not our the intersection point that we computed. So that's the first fix. And when we do that, it looks like this. Um, because next thing we need to go is go here, change this to 1. Still looks weird because last piece of error is from copy pasting. So that's something we want to be aware of because a lot of these are kind of repetitive. So you copy these and change it like one little thing. So you want to be aware of. That is, this needs to be changed to X. This needs to be Y. Finally, this needs to be Y. This needs to be X. And now we got what we wanted. Just like I I changed it in between, but yeah, this is what I wanted to go for. Just slightly different to show you. So now I feel like if I go through the vertices real quick, it'll make a lot more sense. So our 0, 0 starts in the middle. Then we go negative zero point 0.5 this way and negative zero point 0.5 up, and that's how you get this vertex. And from here we go back, and then the second vertex B says vertex A, vertex B. So you go negative zero point 0.5 this way, and then we go 0.5 down. And then finally vertex C, we start from here, we go 0.5 this way, 0.5 this way, and that's how we get our triangle. So yeah, so we simulated light rays from our camera to interact with a 3D triangle. Even though I know we just showed 2D right now because of the canvas you have set up. And we calculated which pixels on the canvas correspond to the triangle and colored them red based on the ray intersection. If it's in the triangle, then the pixel is red, and pixel outside are black. So that's it for this video. I hope you guys found this helpful, and it's a good start for your ray tracer. And also, I hope in the beginning, what we covered on how to render an object from Blender, I hope that kind of gets you guys started off. So that way you guys can figure out a way to parse that, and then feed that into your rasterizer engine to render the object. So yeah, thank you.